Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been discussing various pulse width modulation methods for power electronic converters. After a review on all power electronic converters such as DC-DC, AC-DC, multi-level etc., we have now been focusing on 2-level voltage source inverters. So, we are looking at these power electronic converters now. So, for voltage source inverters, again we looked at many of these previous lectures. We looked at sinusoidal modulation, we looked at first selective harmonic elimination and such low frequency techniques, and finally over the last 2-3 classes we have been looking at pulse width modulation, which is assuming a fairly higher frequency. That is, if you have an inverter, the inverter switches, it switches at certain frequency which we call a switching frequency now. So, the switching frequency is sometimes a low value, that is, the ratio of switching frequency to the fundamental frequency is not very high. It may be 5, it may be 7, it may be 9, it may be 15, it may be low number. On the other hand, the switching frequency can be much higher than the maximum modulation frequency, and that is when you go in for these modulation methods such as sine triangle PWM etc. now. And we discussed sine triangle PWM and a few variants of that such as the third harmonic injection. Today we will briefly review third harmonic injection and we will go on to these bus clamping pulse width modulation methods now. Okay. So, now here we have a single phase voltage source inverter. Just to recap, it is a single pole double throw switch, one leg and there is another leg and the poles are connected to the load terminals. Then you have a single phase voltage source inverter realized and you have this modulating and carrier signals going up and down like this. You have this unipolar PWM and second harmonic injection, bus clamping. These are some of those which we had reviewed in the previous classes. Now, if there is any requirement, we can just go back and take a quick look at some of those. Now, we have okay, all right. So, let us just get started with a particular point here, that is, maybe we looked at second harmonic injection in the case of a single phase inverter. What do we do in a single phase in any inverter? We have a sinusoidal voltage and we have comparing it with a high frequency carrier now. So, the idea here is the midpoint potential of that particular leg measured with respect to the DC bus midpoint. So, this potential varies, the average pole voltage, what we call as the average pole voltage varies in a sinusoidal fashion. Now, you vary two average pole voltages. Now, in a two phase inverter, what do you do? In a 2-leg inverter, which is meant for a single phase inverter, you vary one of them in a sinusoidal fashion shown by the red curve. You vary the average pole voltage of the other leg in this fashion as shown by the black curve, and so you get the difference between the two, which is a sinusoidal function, that is what gets applied there now. So, here it is possible for you to inject a small amount of common mode voltage, though there is no specific advantage in doing that and there could possibly be certain disadvantages also. Maybe, but you can see that it is possible to add such a common mode voltage. This blue thing is added both to the red sinusoid and also to the black sinusoid. So, that is a common mode component. The resultant is this red distorted waveform, which is basically the fundamental plus second harmonic, and here also there is fundamental plus the second harmonic now. These second harmonics get subtracted, that is when you do a subtraction of this red curve. So, this is how the average pole voltage varies in one leg, and like the black curve is how the average pole voltage varies in the other. If you take the difference between the two, this what is common between the two, that goes off and you get only a sinusoidal voltage at the output. Now, this is not very useful as an idea in single phase inverters, but this is extremely helpful in a 3-phase inverter, as we would see, as we have already seen also and briefly reviewed today. So, sometimes you can add your common mode component as shown here, for example, that leads to bus clamping. That is, what we are saying is, in this part the A leg is not switching, here the A leg is switching. Therefore, similarly the B leg is not switching here and it is switching here, right. So, what is going to happen is, as I was pointing out to you earlier, the A leg, there is A top device is going to be conducting, it is going to suffer a greater amount of conduction loss than the A bottom. Similarly, here also the B top is going to conduct than the B bottom device. So, there is going to be unequal heating of the devices, this is an objection now, and we modified this and showed that you can probably think of some common mode injection component like this. This common mode is obtained by subtracting the peak of the carrier from one of the modulating signals. So, for one 90 degree it is one and another 90 degree you use the other signal. and by this you get a common mode component, and this common mode component you add, you get your red waveform. There is one modulating signal. The first 90 degree there is switching, and the next 90 degree it does not switch. Similarly, the black waveform also has a 90 degree interval when it does not switch in every half cycle. So, here it is the top device may be conducting for a long time, here the bottom device would be conducting. So, it kind of balances out, and you really do not have, and you can also see that this common mode component has no average value. So, the top and the bottom devices are equal, I mean their heating is equal, one is not heating much more than what the other is, and so on. And the same way the two legs are also okay. So, there are 4 devices, and all the 4 devices are they get heated up to roughly equal amounts of levels. If one of them gets heated up more than the other, then you are not utilizing the other one very well, that is between 2 devices, let us say top and bottom devices which are equally rated. The top device gets heated more, but the bottom device does not get heated so much. So, you have to stop. What limits your usage? The top device limits your usage. How much power is being handled is limited by the top device. So, the bottom device is not fully utilized. So, that kind of a problem is not here. So, all the devices are equally loaded here. We will deal with this when we calculate switching losses in a much greater fashion now. This is another example of equal loading now. So, this is bus clamping. Now, what we are going to do is, this even harmonic injection has its counterpart third harmonic injection in the 3-phase case, which is what we are going to review and take it to a slightly greater extent, and we are going to look at this bus clamping methods for the 3-phase inverter today now. So, we made certain conclusions out of the addition of even harmonics here, which is there for you to see. You add even harmonics in small measures to the pole voltage, it does not affect the output voltage, and it could lead to bus clamping. And this bus clamping, but if you are doing bus clamping, then you should ensure that the top and the bottom devices are loaded equally, and the 2 devices are loaded equally. This bus clamping can help you reduce certain amount of switching loss, that is one of the purposes now. And if it reduces, here the assumption is your thermal time constant is much longer than the line cycle, because in some part of the line cycle it gets one device gets heated more, in some part it gets heated less, and it averages out, to a lower value than with the normal sinusoidal modulation. Here the inherent assumption is the line cycle is much shorter than the thermal time constant. Alright. The same thing you go on to 3-phase voltage source inverter, the same 3 legs for there for you, every leg represented as a single pole double throw switch. Move on. Now, what do you have? Every leg is represented in terms of 2 devices, the top and the bottom devices, right, which are switched in a complementary fashion. We move on. Now, these are the 3-phase sinusoidal modulating waves, just like a single phase inverter that it has 2 legs. So, you had 2 sinusoids there for the unipolar PWM, and those 2 sinusoids were phase shifted by 180 degrees, 180 is equal to 360 divided by 2. Now, you have 3 legs. So, you have 3 sinusoidal waveforms, all of the same amplitude, same frequency, and they are phase shifted by 120 degrees, 360 divided by 3, right. So, that is what you have. This you can compare with a common triangular carrier which can run up and down and up and down and up and down at a very high frequency, and you switch the leg. So, you switch whether a particular modulating signal is higher than the carrier, the top is on, if it is lower, it is the bottom is on, that is the logic that we have been using. So, you move on. So, as I observed, there are redundancies here, this is what we were been saying the other day. So, what is that redundancy? Now, let us say, as I pointed out the other day, this is a carrier cycle. Now, we are looking at a carrier cycle. A carrier cycle is much smaller than your fundamental line cycle. Because it is much smaller than the fundamental line cycle, what happens? Your sinusoidal signals would look almost like a straight line. Now, let me say this is your MR, it looks like a horizontal line. Now, let me just change the color to maybe green to represent the yellow. Now, this could be your modulating signal corresponding to Y phase. This is a sinusoidal signal, but the sinusoid appears just as a horizontal line within this carrier cycle, or you can consider a particular sample of that sinusoidal signal. Right. Now, let me indicate the blue signal also. Right. This is MB. So, if I am considering sinusoidal modulation, the 3-phase waveforms are 3-phase sinusoidal waveforms, then MR and MY and MB would add up to 0. If there is any common mode addition, then MR and MY and MB will not add up to 0. Their average value will be equal to the common mode voltage now. So, what we mean by this redundancy is the load can be shorted either by all the top devices being on or all the bottom devices being on. So, here itself, as we had observed the other day and repeating today, you have the situation where all the 3 top devices are on, and you have the extreme situation at the last interval where all the 3 bottom devices are on. So, this is one interval, this is other interval, there are 2 intervening intervals. During this interval what happens, your red phase is now switched, it is now plus plus and you mean your blue phase, here the yellow phase y is switched now. So, it goes to plus minus minus now. So, this is how it goes now. So, these are the 2 extreme states now, these are the 2 extreme states, I am sorry, you see this and you see this, all the top are on here, all the bottom are on here. What happens to the load? The load is shorted, that is what it is. So, it does not matter so to the load, but it matters to the inverter, because here the top devices are conducting, here the bottom devices are conducting, right. So, these are called 0 states, because the load voltage is shorted, it is just freewheeling. These are called active states, because there is certain amount of power transfer between the DC side and the AC side during these intervals now. And the line to line voltages are, you will see pulses there. In this case, for example, RY will be 0 and YB will be a positive pulse and BR will be a negative DC pulse. Again, if you look at this interval, you will find that the RY is be positive, YB will be 0 and BR will be negative pulse, that is what you will see. Whereas, if you look at these 2 intervals, VR, VY and VB will all be equal to 0, right. Now, by redundancy we mean here also it is shorted and here also it is shorted, here it is shorted by one switching state, here it is shorted by another switching state. So, the inverter has 2 switching states which both result in shorting of the load. So, this is what we mean by redundancy now. How is this useful? You see that as we told earlier, you know, if the there is a small common mode component is added. Now, let me just go on to the red one, right. Yeah. Okay. Now, let me say I shift the red signal slightly above, I shift the red signal slightly above. What am I going to do with the yellow signal? Now, which I am representing it in green here, this also I am shifting slightly above to the same extent. There are drawing inaccuracies, but please be aware that I am shifting both of them up by the same extent, right. Now, let me go on to the blue signal, correct, right. Here also I am shifting all of them to the same extent. That means, I am adding a common mode signal to all the 3 of them. Now, what is the result of this common mode addition? Because of this, the red signal has been shifted. What has happened here? The red MR and the carrier intersect, but they intersect at a later time. So, you start from here, the red, I mean this carrier is the same, and the first intersection occurs with the blue MB, and MB is now shifted above. Therefore, what happens? The switching instant slightly changes. It is not this previous instant shown in thick line, it is the one that is shown in the discontinuous dotted line. Then the next time it intersects, the carrier intersects with MY. That instant is again shifted. By how much is it shifted? Again it is shifted to the right, it is shifted by the same extent, correct. Then what happens to MR? MR is also shifted up, because of which you have the same situation now. So, all the 3 switching instants are now shifted to the right and by the same extent. If my addition here is not positive, if it were a negative common mode component, all of them would have shifted left now. But what do you find now? Since this switching instant is now shifted to the right, excuse me, I will pick up this arrow, this switching instant is shifted to the right, this is again to the right now, right. So, what is happening? The effective interval for which the active state is applied is not changing. Again the effective interval for this active state is applied is not changing, but the interval for which this 0 state is applied has increased, and at whose expense? At the expense of the time for which this 0 state is applied. So, once again the time for which these 2 0 states are applied together is not different, individually they are different. Now, the sum of these 2 is not the same, is different now. This is what common mode addition results in. You add a small amount of common mode, the one of the 0 state time decreases at the cost of the other. So, as an extreme case, if I add my MR, now let me go back and pick up the red thing again. Now, let us say I add it in such a fashion that my red signal becomes equal to the peak. Similarly, I shift all MY and MB above. Now, what would happen? R phase will be clamped, R phase will not switch at all. So, it is the redundancy of the inverter which allows me to add a common mode component, and I can add a common mode component such that one of the phases is switched now. Let me complete this by indicating what happens to the green also. If I add further, the green will also go up like this, and what will happen to the blue? This will also go up like this. So, all the 3 have gone up, now MR has gone and hit the peak of the triangle, therefore, there is no intersection, it does not compare. MR, this is always high, R phase stop device is always high. So, R phase is clamped. Where is it clamped? It is clamped to the positive DC bus, and therefore, you call it bus clamping. The other thing that you can do is to add a negative common mode component, and how big can the negative component be? It can be so big. The negative component can be as high as this, of course, in the negative direction. So, if you add a negative component equal to the difference between minus V p, that is the negative carrier peak, and M b, then M b will come and hit the negative limit, M y will come down, M r will also come down, but M b comes and hits the negative limit. Again there is no intersection between the carrier and M b. So, now M b is always lower than the carrier in that case. So, that means the B phase bottom device will always be on, and B phase will always connected is clamped. B phase does not switch, it is clamped. It is clamped to what? It is clamped to the negative DC bus. So, when you have a situation like this, when M r is greater than M y greater than M b, it is possible for you to clamp R phase to the positive bus, or it is possible for you to clamp the B phase to the negative bus. So, you try to do one or the other of this. So, the same thing, one thing is possible to do is, since you do it for switching loss, you can see which of the two phases carry higher current, whether R phase carries higher current or B phase carries higher current. So, whichever carries higher current, you can go and clamp. That is one common sense way of doing it now. But what I would like to say is, there are many modulation techniques which have come out of this possibility, which is what we have been discussing now. So, one of them is about this third harmonic injection, where you are adding a third harmonic component to the parent sine wave. We also discussed it earlier. Now, if I write down the equations for that, you have MR, MR is going to be Vm sin omega t. This is what it is in the sinusoidal modulation. My is sin of omega t minus 120, and Mb is Vm times sin of omega t minus 240. This is what is in the case of sinusoidal modulation. How different is third harmonic injection? You add certain common mode component to all the three and call that as Mr star, My star and Mb star. What is the common mode component? You take it as some Vm sin omega t, a fraction of that, k times Vm sin omega t. Here also you add the, I am sorry, this is k times Vm sin of 3 omega t. This is a third harmonic component, and what is its amplitude? It is a fraction of Vm. Now, this fraction can be 0.05, 0.1, 0.16, so on like that. So, this is also the same k times Vm sin 3 omega t. Here also it is the k Vm sin 3 omega t. So, this is what is called as the common mode component. This is what is called as the common mode component. The common mode component is a third harmonic. It is a natural thing. If you add a third harmonic to the sine and phase shift this Mr star by 120 degree, you will get My star. Now, the third harmonic phase shifting by 120 degree for the third harmonic is one cycle now. If you subtract Mr star minus My star, the third harmonic components will go away from there. So, you get this kind of now. So, this is third harmonic injection, and different values of k are possible now. Last time we saw k is equal to 1 by 6. We saw this k is equal to 1 by 6, and this k is equal to 1 by 6 gives you maximum AC voltage with a given DC bus voltage. I have this thing with me, I can show this to you. So, this is what is k is equal to 1 by 6 now. Now, what I have here, the original sine wave, this original sine wave, the red dotted line, that is now I have drawn it for m is equal to 2 by root 3. It is 2 by root 3 times V peak. 2 by root 3 is roughly 1.15. It is 1.15 times V peak now. With that, when I add 1/6 amplitude third harmonic component, it is like this now. So, this amplitude is 1.15 divided by 6 is something like 0.2, little lower than 0.2. That is what you find here now. When I have added this common mode to all the three, what I am getting here is the sine function, the modulating signal, its head goes down a little, it heads bends down a little. So, instead of this it is coming down like this, and here again it goes down like this now. So, what happens now? This is my peak. Earlier, if you consider the original sine wave was greater than the peak of the triangle, and there was no comparison between the triangle and this thing. So, the top device will always be on in such kind of situation, that would be called over modulation, that is not sinusoidal modulation. It will introduce lots of distortions in the current now, because the average pole voltage would not be a sinusoidal signal. How would the average pole voltage be? If I take the dotted red line and compare it with the triangle and switch my inverter, the average pole voltage would vary like this as per this dotted line up to this point, but it can't go above that, because the average pole voltage can't go above VDC by 2. VDC by 2 is the maximum limit when the top device is fully on. So, it gets clipped like that, it would get clipped and then it would come down like this now. So, you apply a sinusoidal voltage, but your average pole voltage is not sinusoidal actually, your average sinusoidal will be a clipped sine wave. Here also it will be a clipped sine wave. The same thing it will be in the B phase and Y phase and B phase also. Now, if you have added the third harmonic component, what has happened is, though the peak of the sine is 1.15 or so, the peak of the modulating signal is just 1. So, it does not go beyond that, and now this is your average pole voltage, this is your average pole voltage. You can see that it is always within the limit of VDC by 2. And what is your Y phase average pole voltage? As shown by this green curve with a bent head here, and the B phase average pole voltage, it is like this now. What is going to be your R to Y average line to line voltage? It is the average pole voltage of R phase minus average pole voltage of Y phase. When you subtract these two, the common mode component given by this blue dotted signal will go, dash will go, and what you will get is only pure sinusoidal waveform. So, you can get, without resorting to pulse dropping or over modulation, you can extend your voltage, you can get more 15% more line voltage, because this is up to 15% more now. So, that is what is, there is an advantage, and k is equal to 1 by 6 has been found to be the optimal value. I will just tell you a little later how to find out this optimal value formally, but this has been found to be the optimal value that gives you the highest value of AC side voltage for a given DC bus voltage. Now, let us say you have a DC bus voltage, let us say it is 600 volts, and you want the maximum line side voltage possible without going into over modulation. Then what you need to do is, you have to take, and you want to do third harmonic injection. Then the amplitude of third harmonic that you should inject should be 1/6 of the amplitude of the fundamental. Another variant of this is I have given as k is equal to 1 by 4. Here 1/4 of the amplitude is added now. I have taken a fundamental component, I am shown that to be something like 1.1. Okay. Onto this 1.1 I am adding a sine component like before, this is a third harmonic sine wave, and how is this third harmonic sine wave? This third harmonic sine wave is 1/4 the amplitude of the top now. When I am adding this, once again I am getting the head is coming down now. You can actually see there are differences between these two. You see here it is somewhere, the peaks are occurring somewhere close to 60 degrees or so, and here you see the peak of the waveforms are occurring a little farther from those angles now. So, depending on what percentage of third harmonic you add, the where exactly peak occurs changes a little. Okay. So, there is some difference it makes. So, what is the speciality of 1 by 4? You can actually add 1 by 8 also, 1 by 7 also, anything k you can choose to be anything within a small number, within a small range, that is all. So, the resultant waveform should not go above, that is one reason now. K equals 1 by 4 has been found to be optimal in terms of harmonic distortion. What do I mean by that? When I use this modulating signal, that sinusoidal signal, and add 1 by 4th amplitude, I get the resultant modulating signal, I do the modulation. Now, I will get some harmonic distortion, I will get certain amount of RMS current in ripple current in my line currents. That is lower for k equals 1 by 4 than it is for k equals 1 by 8 or k equals 1 by 6. So, it has been found to be optimal. That what really it does there is internally, it divides these two 0 state times equally, plus 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 and minus minus minus, it makes them more or less equal, that is what it does. This is what another technique called conventional space vector PWM does much more naturally, which we will see when we start with space vector based modulation, and it is also possible to get this closer. Okay, but one thing that I just want to point out is, the choice of k, you go in for one common choice of k is 1 by 6, which will give you the highest line side voltage, and k equals 1 by 4, which would give you the best harmonic distortion. In fact, conventional space vector PWM, as we will see, combines the advantages of both. It would give a THD as low as that of this k is equal to 1 by 4, and a AC side voltage as high as that of 1 by k equals 1 by 6. You will see that a little later in 1 or 2 lectures later now. So, regarding third harmonic injection, the points that I would like to say here is, now you have this, now you have your MR star is equal to Vm sin omega t plus you have k times Vm sin 3 omega t. So, what this k can be is another issue now. So, as I told you, the waveform peak occurs at different places. So, now you see this is how there the peak occurs here. In this waveform you can see that the peak occurs here and here, it is symmetric, okay, but the angle at which it occurs, it looks to be it is 50 degrees, it is somewhere around 50 degrees now, whereas in the previous case it looks to be around 60 degrees. Okay. So, where the peak occurs is different now. How can you find out where the peak occurs? Simple, as you would all know, all that you need to do is you do this dmr star upon d omega t and equate it to 0. If you do this, you will get omega t peak. You will get the instant at which the mr star has a peak value. Let us call that instant as omega t peak. So, this is once you have this omega t peak. So, at omega t peak you can say that mr star at omega t peak, what is its maximum value? This maximum value can be all the way up to V p. So, this will give you, this will tell you how much is the maximum possible V m. This will give you the maximum possible V m for a particular value of k. For example, let me say I take this k as 0.1 and I go doing about this analysis. I say 0.1 sin omega t. What do I do? D by d omega t of mr star is equal to 0. That would give me the omega t peak, the theta peak, or the instant at which my function goes to a maximum value. So, that will happen twice, when in the positive half cycle, it will happen in the first quarter cycle, and also it will happen in the next quarter cycle now. So, I can find out this instant omega t peak, I can find out this instant omega t peak, right. Once I find out that instant omega t peak, I can say that that is the highest value of mr star, that can go as high as V p. It cannot go beyond that, but it can go as high as V p. So, when I equate that, it is the maximum value, that I will get whatever is the maximum possible value of V m for that particular k. So, you will see that if you take your k to be 1 by 6, then this maximum possible V m will turn out to be 2 by root 3. For all the other cases, it will be somewhere between 1 and 2 by root 3. This is 2 by root 3, it is not very clear. Okay. This is something like 2 by root 3 is what you are going to have now. That is the maximum possible with k is equal to 1 by 6. If you go to k equals 1 by 4, you will get a number which is lower than 2 by root 3, right. So, this is about third harmonic injection, and let us go into the bus clamping PWM. As I said, in the third harmonic injection and the bus clamping, third harmonic you are adding a third harmonic component, right. That is, you are adding mr star, this is V m sin omega t is the original mr, plus you are adding a common mode component. Again for my star also you do the same thing, this is V m sin of omega t minus 120 plus the same common mode component is there. MB star is equal to V m sin of omega t plus 120 plus this common mode component. Now, what is this common mode component is the question. In the case of third harmonic injection, the common mode component was a third harmonic component V m sin omega t, k times V m sin omega t. Now, you can choose an MCM such that it would clamp the bus, it would clamp one of the phases. Now, for example, let me take this. Can I clamp R phase? Yes, I can clamp R phase. When can I clamp R phase? Now, to which bus? It could be to the positive bus or negative bus. When can I clamp it to the positive bus? When out of the 3 signals mr star, my star and mb star, or mr, my and mb, these are mr, my and mb, out of the 3 sinusoidal signals, when mr happens to be the most positive signal, then it is possible for me to clamp R phase to the positive bus. Similarly, if mr turns out to be the most negative signal out of these 3, then I could possibly clamp R phase to the negative thing. So, how can I clamp mr star to the positive bus? Now, let us say mr star V m sin omega t, let us take omega t is equal to 90 degrees or something very close to that. So, this is equal to V m, mr is equal to V m plus MCM. So, you want it to clamp. So, what do? You must take the difference between V peak and mr. You take the difference between V peak and mr. Now, for example, I can say MCM is equal to V peak minus mr. When in the region, let us say 60 less than omega t less than 120. This is when R phase goes through the peak, at 90 degrees it goes through the peak, between 60 to 120 it is the most positive of the 3 sinusoidal modulating signals. So, you can pick up MR, subtract Vp, Vp minus MR, you can treat this as the common mode signal. If you add the common mode signal to all the 3 quantities, what will happen? Your MR star, this would imply your MR star is equal to Vp when in this range, Okay. So, in the next thing between 120 to 180 you will pick the next phase, and between 180 and 240 you will pick the next phase. That is how you get your one of the first bus clamping PWM methods, which we call as a 60 degree clamping method. Now, you can see that this is, as I pointed out earlier, R phase has been clamped here, because how is the common mode been derived? The common mode has been derived as the difference between Vp and MR. So, this is the common mode signal now. And the next time what I am doing? This is the common mode signal, the B phase is getting clamped now. How is the common mode been derived? As the difference between minus Vp and the B phase is sinusoidal signal, that is the common mode component here. And again see, you see the common mode component goes like this, and you can see that the common mode component is a triple frequency component. The fundamental frequency of the component is, now if you look at it, see this is 60 degrees, this is 100 and another 60 degrees. So, from here to here is 120 degrees now. So, this common mode component has a fundamental frequency that is equal to 3 times the fundamental frequency. So, it is a triple, it has all triplen frequency components. It has third harmonic, not only third harmonic, it has 9th harmonic, it has 15th harmonic, it has 21st harmonic, and it has all of them. It has only the odd harmonics in this case, because they are only these, there is half wave symmetry here. This has only 3rd, 9th, 15th, 21st and all these harmonics it really has and goes in the class, it goes on. So, you are adding them. Now, if you once you add, you get this resultant signal, this is your red phase signal, and what is your yellow phase signal shown by the green line here. So, both of them have the original sinusoid plus the common mode added. So, your red phase pole voltage, the midpoint average pole voltage measured with respect to the DC bus neutral has this wave shape shown by the red modulating signal. The yellow phase has again the wave shape shown by the green modulating signal, right. The difference between the two is only a sinusoidal signal. So, what gets applied as VRY, the average voltage of VRY will be a sinusoidal signal, this will not be there now. So, this is why you call it bus clamping, because R phase is clamped to the positive bus, here B phase is clamped to the negative bus, Y phase is clamped to the positive bus, R phase is clamped to the negative bus, and it goes on like that now. We call it 60 degree clamp. Why? Because it is clamped in the middle 60 degree duration, it is just a name that we are giving. You also find various other names available in the literature, because it is clamped for the middle 60 degree duration in every half cycle. Now, in the positive half cycle it is clamped to the positive DC bus in the middle 60 duration. In the negative half cycle, for the middle 60 degree durations it is clamped to the negative bus. So, we just give a name called 60 degree clamp in this course for this now. So, this is one possible clamp, not all possibility now. And also the other name given is a discontinuous modulation. The discontinuous PWM is more commonly used here. Why is it called discontinuous PWM? If you look at the modulating signal, this is the modulating signal. Now, this modulating, the original sine wave is a continuous function of time, it is sine omega t, it is a continuous function of time, but the common mode that you are adding is a discontinuous function of time, and the sum of these two, which is the actual modulating function, is a discontinuous function of time. You see there is a discontinuity here, you see there is a discontinuity here, you see there is a discontinuity here, there is a discontinuity once in every 60 degrees in this particular case. Because of these discontinuities, it is called a discontinuous modulation scheme, or discontinuous PWM is the other term used for bus clamping PWM. Now, the same 60 degree PWM, as I was saying, what would be the advantage? One of the advantage we have already said, which I am repeating, is now the peak it goes, how much does it touch? Now, I have taken a peak, how high is that? It is 1.15, that is 2 by root 3, as high as I considered for the THA PWM with k is equal to 1 by 6. So, now what is happening? You see that in this signal looks qualitatively different. As the fundamental peak goes on increasing, what will happen is this sign will come down, and when the fundamental crosses 1, this will look different, the common mode component will look different, like shown here. Now, this is a case where it is the highest possible fundamental voltage I have drawn. Now, you see that for this is the common mode component. When I add the common mode component, what happens is the waveform goes between 60 to 120, it is still clamped, and then it is down. It is, this part is not sinusoidal, this dotted line is sinusoid, but the solid line is not sinusoid, and here it is flat, and here. What is the difference between the dotted line and this sine, this wave, which is sine looking wave, it is not really sine wave. This is the difference of sin omega t minus 1, that is I mean 1.15 sin omega t minus 1 is what it is now. So, you have this waveform and you add this now. So, you are able to accommodate a sine wave up to 2 by root 3, that is 1.1547. So, you get 15% more fundamental voltage, that is one of the advantages as high as in the third harmonic injection with k equals 1 by 6. The other advantage you can get is, of course, you are not switching for 1/3 of the cycle. Therefore, the switching loss can be reduced now, and the conduction loss, here you see the positive device will take more amount of heating, that is will get heated more because of continuous conduction. The same way the bottom device in that R phase leg will conduct continuously here and will get heated up. So, they get heated to an equal extent. If you look over a fundamental cycle, they get heated to an equal extent now. So, it is distributed. Again here the assumption is the line frequency, the line cycle is much shorter than the thermal time constant. So, it takes a long while for the heat to get distributed. So, you have this kind of an assumption here. You have these waveforms. So, one advantage is that you can get a higher fundamental voltage. Another advantage is you can possibly reduce the switching loss. But if you see, the switching loss can be considerably reduced only if the phase current also has its peak in this side, if the R phase current also has its peak in this region. If R phase current is going through a 0 crossing here, not much saving is obtained, and R phase for example has its peak here, when R phase is switching, not much is obtained here. So, you have this thing of phase shifting which you can normally do. So, now for example, if the R phase in this case, let us say it is leading, the current is a little leading, then you can go in for a clamping as shown here now. So, this part can be clamped. Here also it is clamped for 60 degree duration, for continually you are clamping now. So, if the phase is leading, in case the phase is lagging, you can clamp like this, where you can see that here in this case the R phase is clamped between 90 degree and 150 degree now. So, this is another example of what we call as continual clamp PWM. Why do we call it continual clamp PWM? In all these cases from here or here, this is the same thing, or here, a phase is getting clamped continually for a 60 degree duration. That is what you can clamp it for. If you clamp it for 120 degree duration, there will be an uneven loading of the top and bottom devices. So, it is clamped continually. Alternatively, this 60 degree duration can be split into two parts, and that is what we would call as split clamp PWM in the next few slides now. So, this is continual clamp PWM, and the clamping can be for a 60 degree duration. The 60 degree duration can start as early as 30 degrees and end with 90 degrees, or it can start at 40 and end with 100 degrees, 50 to 110. The other extreme is 90 to 150 degrees. So, anywhere between 30 to 150 you can place this 60 degree interval, and it is done symmetrically in all the phases now. So, these are some examples of continuous clamp PWM that I have given here now. So, you have all these examples that it is clamped as it goes now. So, the other thing is, if you want to break it, the continuous 60 degree clamp duration can be broken into two parts, what I am calling as 30 degree clamp here. If you see here, this phase is clamped, the R phase is clamped here. What is the kind of modulating signal? The modulating signal is this blue signal going up and down, and there is a discontinuity here, and down and up, there is a discontinuity here, then up and down, and then there is a discontinuity here, then down and up, discontinuity here. This is the nature of the modulating signal. This modulating signal, if you add to this, you get that R phase is clamped for 30 degrees here, between 30 to 60 degrees, and here again it is clamped for 120 to 150 degree. So, this 30 to 60 is the middle 30 degree duration in the first quarter cycle. Again this 120 to 150 is the middle 30 degree duration in the next quarter cycle. So, every phase is clamped for 30 degree duration in the middle of every quarter cycle, and that is why we give a name called 30 degree clamp PWM. Again this is only a name, there are different names are used for these methods, and we call it 30 degree clamp PWM because every phase is clamped this way, the middle 30 degree in every one of this now. So, this 30 degree clamp is a special case of split clamp PWM. That is what has not commonly been realized. In fact, it is not, the 60 degree duration has been broken into 30 plus 30. Should it be broken only as 30 plus 30? Can it not be broken as 45 plus 15, or can it not be broken as 15 plus 45? Yes, it can be done, and the more general case is what we would call as split clamp PWM. Now, this is an example where you start clamping again at 30 degrees, but this is not going all the way to 60 degrees here. It stops at 42 degrees or 45 degrees or something like that, 42 degrees maybe. and the remaining duration, let us say if you have clamped for 12 degrees here, for the remaining 48 degrees you clamp it here. It is a little difficult to see this possibility, but this possibility exists and this has not been thoroughly discussed. It is only in a very few recent papers you find this possibility kind of getting discussed, whereas this possibility has been commonly seen now. Okay. So, now this is also possible that you have this now, and this is actually advantageous in certain lagging power factor situations from the point of view of switching loss, as we will come to later now. Let me first clear up all the possibilities now. So, this is a case where it is clamped for something like 12 degrees here and let us say 48 degrees here. So, that is one possibility. Now, I am showing another possibility here where it is clamped for something like 45 degrees here maybe, and it is clamped only for 15 degrees here. This is the R phase signal now. So, the 60 degree duration is clamped into two intervals, and one interval falling in the first quarter cycle and the other interval falling in the second quarter cycle of every half cycle of every phase now. So, you call it split clamp PWM. How do you generate this? How do you generate this? For continual clamp, you take one particular sine wave. You are seeing the difference between the sine wave and V peak, and that is what is added as the common mode component. In the case of split clamp, what you do is between 30 and 60 degree, where you are clamping R phase for example, the common mode signal is really the difference between Vp and Mr, and in the next thing what is getting clamped, it is the Y phase. So, the common mode signal is nothing but the difference between minus Vp and this signal, and similarly here the blue phase, this other phase is getting clamped. So, here it is this and minus Vp, the difference between the two is the common mode signal, and once again you go back to R phase. So, between 30 to 60 and 120 to 150 you use R phase signal. Your common mode is Vp minus Mr, and then this is done symmetrically for the other phases and on the other side, the negative side also. You are getting that. So, this is how you get a 30 degree clamp, and the generalization of this is you do not have to clamp from 30 to 60 and 120 to 150. You can clamp it from 30 to some 30 plus gamma and some 150 minus gamma to 150, where gamma can be anything between 0 and 30 degrees. So, this is a case where gamma is some 12 degrees. So, this is clamped from 30 to 42 degrees, and here it is clamped from, this is 150 minus gamma is something like 102 degrees, some 102 degrees to 150 degrees you have a clamp here now. The other example that I am illustrating here is, here gamma is something like 45 degrees. So, from 30 you are clamping till 75 degrees here, and what you do here, this is for remaining 15 degrees up to 150, 135 to 150 now. So, the split clamp PWM has been found to be more advantageous than continual clamp PWM in terms of harmonic distortion, which we will see in later lectures when we go into analysis of current ripple. So, this continuous clamp, any of this continual clamp PWM methods you take, and you take any of the split clamping PWM method, you will find that the split clamp PWM method results in a lower harmonic distortion than the continual clamp. That is one advantage of that. The next advantage is really in terms of the switching losses. Continual clamp is suited for, I am just stating it now, I can't prove it now, I will prove it when we do the real analysis, when we really work out the switching losses and conduction losses in the inverter. I am saying that this continual clamp is advantageous when the power factor is high. I will illustrate it very easily. So, now let me take the 60 degree clamp PWM method. So, when the power factor is high, that is when the power factor is unity. So, this is your sine, this is the fundamental voltage, this sine represents the fundamental voltage. If your power factor is unity, again your fundamental current will be like this, and the current will have its peak close to the voltage peak now. So, whenever the R phase current is going through 0, the phase is not switching, and switching energy lost is proportional to the current it is being switching. So, the phase is keeping quiet, it is not switching when the current is going high, and therefore, there is a substantial reduction there now. On the other hand, if it is not a unity power factor load, let us say if it is a lagging power factor load, if it is a lagging power factor load, then this kind of a continual clamp is helpful now. Okay. So, there are many examples, and if it is a leading power factor load, then you can adjust this. So, this position of 60 degree has been adjustable, that is sometimes called generalized discontinuous clamping or generalized bus clamping PWM method, and more advanced versions have also been derived from this now. This is split clamping, a particular case of split clamping where you are clamping it for 30 degree duration. This is a more general case where you are clamping it for gamma and another 60 minus gamma, gamma in one quarter cycle starting from 30 degree and 60 minus gamma in the other quarter cycle ending with 150 degrees. This is your split clamp PWM now. And the split clamp turns out to be advantageous when you are talking of low power factors. the inverter operates at a very high power factor. For example, when you are active front end converter etc., some applications you do, it is a UPF rectifier. So, something like a 60 degree clamp could be better there, whereas if it is like a STATCOM where reactive current is being given, a 30 degree clamp is possibly a good option there. For low power factors, when the power factor angle can be 80 degrees or so, such kind of split clamp PWM methods are found to be better, as we will also see in this particular course now, right. So, let us say a few more words on continual clamp and split clamp now. In both the cases, what you are doing is you are clamping a phase for 60 degree duration. So, 60 degrees duration, what is being done? Clamping a phase, where? To a particular DC bus, to a particular DC bus. Now, for example, R phase maybe to DC bus. What is the duration? The duration can be some 60 plus gamma to 120 plus gamma. This is the duration, and gamma can be anywhere between minus 30 degree to plus 30 degree, minus 30 degree less than gamma less than plus 30 degree. So, if it is minus 30 degree, the clamping is between 30 to 90. If it is plus 30 degree, the clamping is between 90 to 150. If gamma is 0, it is between 60 to 120. Gamma can take any value in this range now, and this is, you call it as a continual clamping, because it is clamped continuously for 60 degree duration now. Then on the other hand, if you have split clamping, what you are doing is the 60 degree duration is broken into two parts, say some 30 degree comma 30 plus gamma is one possibility, and 150 minus gamma to gamma. Is it right, or is there a mistake here? That is, here it is for a duration of gamma, here it is, yeah, I am sorry. This duration ends with 150 degree, and this is for a 60 minus gamma. 150 minus of 60 minus gamma is 160, is actually 90 plus gamma. So, this is 90 plus gamma. So, this is the duration for which it is clamped. So, for this R phase is clamped, R phase clamped to positive DC bus. Let us look at the 3 phase, if you look at 3 phase sinusoidal waveform somewhere, that will make things clearer. We have an option, R phase for example, you can clamp it between here and here, you can clamp to the positive DC bus. Now, if you take this interval, R can be clamped to the positive DC bus, here also R can be clamped to the positive DC bus. You take the next 60 degree interval, Y phase can be clamped to the negative DC bus, you take the next 60 degree interval, B phase can be clamped to the negative DC bus now. So, you have the situation where the most positive can be clamped to the positive bus and the most negative can be clamped to the negative bus. So, if you take this 30 to 90 degree duration, R can be clamped to the positive bus or Y can be clamped to the negative bus. R 90 to 150, if you take, R to the positive bus is possible or B to the negative bus is possible now. So, there is an option now. For example, if you are between this 90 to 150, whether you want to clamp R phase to the positive bus or clamp B phase to the negative bus is an option now. This option is what results doing this now. In the case of continual clamp, what are you doing? You are clamping for some 60 degree durations here in the middle of this. You are choosing a 60 degree duration to be somewhere in the middle, and in the remaining part you are letting this Y phase to be clamped to negative, and you are, I am sorry, and you are letting the B phase to be clamped to the negative now. In the case of split phase, what you are doing is there is some interval here at the start, you are clamping it to the R phase to the positive, again some interval to the end, you are clamping it to the positive, and in between what you are doing is in this region you are clamping Y phase to the negative bus, here you are clamping, I am sorry, B phase to the negative bus. So, this is what is really being done. There are two options, clamping one to the positive, clamping one to the negative. You are exercising these two options, and so you have this kind of situation now. So, this is about our continual and split clamp PWM method. Now, there are various examples, you can look at more of this in one of the references that I can possibly give you. There are some recent papers, and one of them this particular paper by Zhao, Pawan Kumar, Narayanan and INR, It discusses space vector based hybrid pulse width modulation techniques for reduced harmonic distortion and switching loss. This paper essentially talks of certain advanced bus clamping PWM methods, which we have not covered till now, which we will cover at a later date. But in the run up to that, the paper also discusses the bus clamping PWM methods, and where it discusses this continual clamping and split clamping methods. Now, these clamping methods are very widely known. Particularly what we discussed as 60-degree clamp is probably most universally known, and 30-degree clamp is also known equally well, has been widely used there. But the only thing is that 60-degree clamp can be generalized to continual clamp, which is also being done. Again, the 30-degree clamp to be generalized to split clamping, which is also possible. You can see this continual clamping and split clamping much more easily when we deal with the problem of bus clamping PWM from the space vector domain. In the next few lectures, what we will do is we will move over to the space vector domain, and we will start generating PWM, start looking at PWM generation from the space vector point of view. That point it will be very clear for you as to how to come up, I mean these two possibilities of continual clamp and split clamp will be much easier to see now. So, let me just finish off a few more things when I write this now. So, let us be very clear as to what we are doing. In all these cases, as I said, we are adding a common mode component. We are adding a common MR star is equal to MR plus MCM, where MR is the original sine wave Vm sin omega t. Similarly, you are adding that to, so My star if you take is also equal to My plus MCM and so on, and you also have Mb star is equal to Mb plus MCM. So, what you really have is, now if you look at the average pole voltage, that is pole meaning the midpoint of this. So, V R O measured with respect to the midpoint and its average value, average meaning this VRO is averaged over a half carrier cycle. If you do that, what you are going to get here is, this is going to be MR star upon Vp times Vdc by 2. This is what you will get now. So, what will be your VYO average? VYO average will be similarly My star by Vp times Vdc by 2. So, VYO average is equal to M y star times M y star divided by Vp times Vdc by 2. The same way you have VBO average also, which I am not writing down. If I want to get VRN average, this N being the load neutral, also R phase voltage now measured with respect to the load neutral. The load neutral is not electrically connected everywhere. So, if anywhere. So, VRN average I will get it as of VRO average minus VYO average. You do it as 1/3 of VRO average minus VYO average. So, this is my VR, I am sorry, yeah, this is VRY average minus VBR average. That is, you subtract these two, VRO average and VYO average, you subtract VRO average and VYO average, you will get VRY average. Similarly, if you subtract VBO average and VRO average, you will get VBR average. Now, if you take VRY average minus VBR average, you take 1/3 of that, you are going to result in VRN average now. So, when you do a VRY average itself, now let me just clear up this part to discuss that. I am sorry. Okay. Now, let us say right. So, I will have my VRY average and VYB average. Let me write down the expression for VRY average here. What is VRY average? VRY average is going to be VRO average minus VYO average. So, VRO average minus VYO average is what? I will have the same thing, MR star minus MY star. This is simply equal to MR star minus My star divided by Vp times Vdc by 2. So, MR star minus My star is what? MR star as MR plus MCM, MR star is MR plus MCM, MY star is MY plus MCM. So, MCM gets cancelled here. What happens is simply MR minus MY. So, this is just MR minus MY times by Vp times Vdc by 2. Let me just write that if you need that too. Sorry. So, this is MR minus My by Vp times Vdc by 2. So, the line to line voltage does not have a common mode component, but you have the advantage that MR can go greater than 1. It can go all the way up to, I mean the peak value, its MR's peak value or MY's peak value can go all the way up to 2 by root 3. So, that is one significant advantage of doing this bus clamping. The other advantage, so you see that is not the, whatever common mode is added here, the common mode is there in the average pole voltage, it is there in the modulating signals, it is there in the average pole voltage, but this is the average line voltage, Ry is the line to line. So, this line to line voltage is averaged over a half carrier cycle is Vry average, that is Vry average minus Vy average. So, this has a common mode component, that has a common mode, they get cancelled out. That is what is there in MR star and My star, they get cancelled out. So, you get MR minus My times Vp by Vdc by 2. So, the average line to line voltage does not have any common mode component, and if you consider the load to be a 3 phase star connected load as Ryb with a load neutral N, and the load neutral N is not connected anywhere and the load is balanced, then you can write this Vrn average in terms of Vry average and Vbr average, because your Vrn is actually equal to Vry minus Vbr 1/3 of that. So, Vrn average is 1/3 of Vry average minus Vbr average. If you do this, you will go back to what is your Vro average now. If I write this really down, what I would get here is this would turn out to be simply MR by Vp times Vdc by 2, goes back to the original equation MR by Vp times Vdc by 2. It is just same as Vro average without the common mode component added there, without the common mode component added. The only difference is now your MR can go much greater than 1, that is what accounts for the DC. So, all these bus clamping methods can give you a very good DC bus utilization. They can also save the switching losses, but that depends on the power factor. You should know to choose the correct PWM method for the correct power factor, then it can also result in substantial saving in switching loss. And among the methods, there is continual clamp and the split clamp are two broad categories now, and split clamp is a little better in terms of the continual clamp in terms of harmonic distortion. So, these are the remarks that I would like to make, and I would I hope that you enjoyed this lecture, and I look forward to your continued interest in the subsequent lectures when we will discuss further PWM methods. Thank you very much.